Section 12.3, Double Integrals in Polar Coordinates, Video 1. Before we get into actually setting up and evaluating double integrals in polar coordinates, I think it would be a good idea to quickly review the relationship between polar coordinates and rectangular coordinates. Recall that rectangular coordinates are the coordinates that most people are familiar with, the x and the y. What's the what's the horizontal displacement from the origin, and what's the vertical displacement from the origin, your x and your y. But for polar coordinates, to get from the origin, or in polar coordinates, it's called the pole, to a point in the plane, we get there by first rotating a certain angle, and remember that rotating counterclockwise is a positive angle, and rotating clockwise is a negative angle. But to get to a point, we rotate a certain angle, which we're going to call theta, and then we travel a certain distance called r. In polar coordinates, the r, the radius, can be positive or negative. A positive radius basically means after you're done rotating, walk forwards, and a negative radius would mean after rotating, walk backwards. Because of the fact that we can rotate as many circles as we want, and the fact that a radius can go both forwards and backwards, there are an infinite number of ways to represent the polar coordinates for a point, as opposed to rectangular coordinates being unique. In other words, to get to the point x comma y, we only have one way to do it. Go over, go up, and that's it. But for polar coordinates, we could rotate the angle plus another complete revolution, so plus 360 in degrees. Wait a minute, we're in calculus, nothing is in degrees. Plus another 2 pi, or plus another 2 pi, or plus another 2 pi, and then go the standard radius. Or we could rotate the angle theta, go a half revolution, negative pi, and if we did that, we would, did I say negative pi? Just pi. Rotate whatever angle you want, plus another half revolution, which would be pi, but we would be facing the wrong direction, so we could have a negative radius to go backwards. And again, we could do as many revolutions plus a half and have a negative radius. So just keep in mind that the polar coordinates for a point in the plane are not uniquely defined. There are an infinite number of ways to represent it. In order to convert between rectangular and polar, we basically just have to do basic trigonometry on this triangle. If we're converting from rectangular to polar, that means that we know the x and the y, and we want to know the r and the theta. The Pythagorean theorem nicely ties together the x, the y, and the r, but if we want to know what r equals, we would square root both sides. However, keep in mind that if we were to not square root the Pythagorean relation, that gives us another relationship between x, y, and r. So when we're converting from rectangular to polar, anywhere you see an x squared plus a y squared, you can replace it with an r squared. To get the angle, we would just have to set up a relationship between the angle and the x and the y, and that would be tangent. But if we want to know what theta equals, then we would have to do the inverse tangent of y over x. Be very careful when you're converting from rectangular to polar when you're finding the angle, because as a function, inverse tangent has a limited range. Without reteaching trigonometry, when you do inverse tangent, say in a calculator, it will only give you a value in this interval between negative pi over 2 and pi over 2, or negative 90 degrees and positive 90 degrees. So if your point is in quadrant 2 or 3, and you're attempting to find the angle for the polar coordinates, your calculator would give you the incorrect angle. How would you adjust it? You would just add a half revolution to it, add pi over 2. When I'm teaching this, I will usually say asterisk, and the asterisk will say add pi over 2 if x is less than 0. Why would that matter? Because if x is less than 0, that means that your point is back here, either in quadrant 2 or 3, but your inverse tangent function would only give you an angle in quadrant 1 or 4, so it would be off by a half revolution. Now, if you're converting from polar to rectangular, Then there's a couple of other easier equations where you don't have to worry about anything. If I know the r and the theta, and I want to figure out x, the trig function that ties all these together is cosine. Cosine is adjacent over hypotenuse. So cosine of theta is x over r. If you multiply both sides of that equation by r, you get this conversion. And for the y-coordinate, in terms of r and theta, the trig function, or a trig function, I should say, that will relate r, theta, and y is sine. The other one is cosecant, but let's not go there. So if we set up sine of theta, it would be y over r, and if we multiplied both sides by r, we would get y equals r sine theta. So converting from polar to rectangular is a little bit more straightforward because you don't have to worry about, oh no, should the radius be positive or negative? And oh no, is this going to be the correct angle, or do I have to add pi over 2 to get it into the correct quadrant? All right, in the next video, we'll talk about how you convert an integral in rectangular coordinates into an integral in polar coordinates. For the most part, it's pretty straightforward with one twist.